Funding for this program was provided by the UCLA Office of Instructional Development.
When I got a phone call from Ernest Wright offering me the Faculty Research Lectureship this year, I was speechless because, as Chancellor Block has mentioned, I don't have that list of honors. In fact, I have to say that this is the greatest honor of my career, and I thank the Academic Senate for this splendid opportunity to show you all the amazing phenomena that we've enjoyed looking into. So, Chancellor Block, members of the Academic Senate, friends and family, thank you for being here, and thank you for sharing this moment with me. On to the science. Let me tell you about some amazing phenomena which happen when just a small amount of energy is injected into various continuous systems, such as liquids and solids. If you have a bubble of gas in water and have it interact with a sound wave, you can generate flashes of light which are hotter than the surface of the sun. If you take a roll of Scotch tape and cause it to peel by simply applying a smooth force, the peeling generates X-rays which are energetic enough and plentiful enough to cause you to be able, in a few seconds, to take an image of the joint in my finger. If you would purchase a crystal of lithium niobate, which is a commonly available ferroelectric crystal, it's used in cell phones, and then supply to this crystal tens of degrees, to heat it by tens of degrees, the stresses generated by the thermal expansion of this crystal generate electric fields which are sufficient to make dangerous amounts of nuclear fusion if surrounding the crystal there are hydrogenic gases. In each of these phenomena, the input of a spread out, smooth distribution of energy is concentrated by some sequence of amazing natural phenomena so as to create these remarkable high energy effects. What I'm showing you here, these phenomena, the data, are not controversial. They have all been reproduced in other scientific laboratories. However, the explanations of all these phenomena are highly controversial. How can that be the case? Isn't physics determined by the first principles of physics? These are written in stone. There is Schrödinger's equation of quantum mechanics. There's Maxwell's equations of electromagnetism. Starting from these equations, it should be a matter of mathematics to arrive at the phenomena that I just showed you. However, these equations are so far from the amazing phenomena that we just discussed that this is the only time today you're going to see any equations. Now, here is an apparatus which is very similar to the apparatus used for the discovery of sonoluminescence in 1934. Mounted on this blue handle is a plate, and when that plate is vibrated up and down, in this case at 1,000,000 cycles a second, the vibrations cause to appear in the liquid bubbles, and then the vibrations also make sound, And the interaction of the bubbles with the sound in this apparatus generate this light, which can be seen when the sonoluminescence signal, which can be seen when you turn out the lights. This apparatus is identical to the apparatus that was used at the 200 building by the physical therapist to treat problems with my rotator cuff. When I first heard about sonoluminescence from my friend, Tom Erber, I said, it's impossible. Tom was great at reading the old papers. And he said, oh, the Germans in 1934 found that if you put sound into a liquid, you get water. And I said, it can't work. The energy scales aren't right. Sonoluminescence is light. The light must come from an atom. If you have the smallest unit of light, which is a photon, coming out of an atom, the energy density is 12 orders of magnitude, a factor of 1 trillion higher. Then the energy density of the sound field, which is just moving up and down throughout the system. So how does the energy focus by a factor of 1 trillion to make the light out of the sound? We can see how unusual the phenomenon of sonoluminescence is by putting it into parallel with Einstein's explanation of the photoelectric effect. In the photoelectric effect, light shines on a piece of metal and kicks out electrons. The energy required to kick out an electron, we know now, is on the order of volts. However, if you have a distributed source of light, such as a 1-watt light bulb, 10 meters from the metal foil, the light is delivering only 10 to the minus 4 electron volts of energy to each atom per second. Now, if the electron has to come out with 1 volt of energy, and if you're getting 10 to the minus 4 per second, it means it takes 10,000 seconds in order to deliver enough light, if you think of light as being spread out, to kick out the electron. But in the experiments, the electrons are kicked out immediately. And of course, the explanation there is that the light must be coming in packets called photons in order to cause this to happen. Here is Tominaga's explanation or interpretation of the photoelectric effect. He says, look, it would take such a long time for the atom to absorb enough energy to kick out an electron unless the atom had a sort of supernatural method of collecting energies instantly from an extended region of space. Sonoluminescence is just that supernatural phenomenon that Tominaga ruled out in order to say that the only explanation of the photoelectric effect is that the light a priori comes in these bunches called photons. Tominaga, by the way, shared the Nobel Prize with Richard Feynman and Julian Schwinger, and Julian Schwinger was the 1980 faculty research lecturer right here. So, how does the vibrating fluid make light? The fundamental principle of physics is if there's light, there are accelerating charges. So how do accelerating charges make light? Well, that's very basic. But how do we then get from a neutral fluid, which is vibrating, to free charges, which are accelerating in order to make light? Somehow, the knowledge of the first principles that accelerating charges make light doesn't lead you or hand you an explanation of the phenomenon of sonoluminescence. You need more. So in order to learn about the sonoluminescence, the goal is to obtain sonoluminescence from the gas of a single bubble. Here, it's hard to see it, but we're going to do a demo. Here's a single bubble. In this case, one sets up a sound field inside of a cylinder. There's a piezoelectric ceramic here. And as the ceramic vibrates up and down due to a voltage, you can trap, You can trap a bubble of gas in the system, and then that bubble of gas pulsates in response to the sound field, expanding during the rarefaction part of the sound field and collapsing during the compressional part of the sound field to emit flashes of light. In this case, you get 30,000 flashes per second, and over here, by shaking this tube up and down, you achieve 40 flashes of light per second at 40 hertz. We have set up a demo of this particular apparatus, and maybe we can switch. Here's Dr. Brian Kappas. We call this his thesis bubble. And we have to turn out the spotlights or something. Yeah. Yeah. No. Yeah. So what you're... yeah. So he's holding a cylinder which is about the size of a test tube. Inside the cylinder, we've made use of Avik-Chakravarty's insight that to optimize the sonoluminescence, you want to have a viscous liquid with a very low vapor pressure. And then in a slight vacuum above the liquid, there's a xenon gas, which is then dissolved into the liquid. As the liquid is shaked up and down, can you see the flashes of light on the screen? Okay. So we'll go back to the... Thank you. Back to the presentation. If you didn't see Brian Kappas in the feed, here he is. And here is a stop-action photo of a single bubble absorbing sound energy, crashing down and emitting a flash of light. And to appreciate the strength of the flash of light, you have to realize that there's a floodlight shining right into the camera while this movie was made. To a physicist, energy and time are very important parameters. Energy and time are conjugate variables. And when I first heard about sonoluminescence, it became imperative to figure out how long are the flashes of light. I was an acoustician working in the lab of Izzy Rudnick, and this experiment required optical equipment. And so I ordered a photomultiplier tube for $300 in order to try to measure the flashes of light of sonoluminescence in an apparatus that Brad Barber had set up. Here is an example of our first data which we acquired with a photomultiplier tube looking at the flashes of light from sonoluminescence. What you have to do is to calibrate the tube. And to calibrate the tube, we used a picosecond light source that was provided to us by Katsushi Arisaka in the high energy group, who also tutored us on the use of photomultiplier tubes. Now, the key property of a photomultiplier tube is the slope of this line. The tube is sitting here quiet, putting out a signal showing that no light is coming in. When the light arrives, the tube responds, and the response is reckoned negative. The slope of this line tells you how fast the tube is responding to the light. And the slope of this line also gives you the price of the tube. This is a standard 2 nanosecond photomultiplier tube. What you can see here, and I need to tell you how a nanosecond is a billionth of a second. A picosecond is a millionth of a second. So here the tube is responding to the picosecond flash of light. Here, the tube is responding to sonoluminescence, and you can see there's no difference in the response, which means that the flashes of light are extremely short, and we got extremely excited that the flashes of light are less than a nanosecond, less than a billionth of a second, in order for these two to be the same. This meant we needed a much faster tube. This meant that we needed much faster electronics to read out that tube. And so we contacted Hewlett-Packard and Hamamatsu and told them, hey, we need to buy this very expensive equipment, which exceeds my credit card limit by a factor of 10. However, before we buy this equipment for these important experiments, we would like to be able to verify that they perform properly in our laboratory. Well, would you believe the equipment showed up and Brad Barber worked the night shift so that he wouldn't be there when they tried to reclaim the equipment. The bottom line is that the flashes of light from sonoluminescence were shorter than 50 picoseconds. Imagine an audible sound field can be used to generate flashes of light that short. The radius of the bubble, as it pulsates to turn sound into light, can be obtained by scattering light off the bubble. This is laser light hitting the bubble. What you need to know is simply that the amount of light scattered by a spherical object goes as the square of its radius. So if you take the light signal and take the square root, you get the radius as a function of time. And here is how sonoluminescence is primed. The bubble expands when the total pressure acting on it is negative. So here's the sine wave. This is the pressure due to the sound field. In addition to that pressure, there's a 1 atmosphere from outside acting on the system. When the 1 atmosphere from outside plus the sound field, which is negative here, is more negative than 0, is below 0, then the bubble expands. But then, as the sound field plus the external ambient pressure becomes positive, the bubble stops being ripped open, but continues to expand due to its inertia. So from here to here is Newton's law of inertia. The bubble keeps expanding like a rocket ship in its radius until it's perched at the maximum radius, and the sound pressure has gone to 0, and there's 1 atmosphere from outside. So you've expanded the volume, you've caused a vacuum, and then the bubble crashes down, and here's where the sonoluminescence is emitted, and the acceleration at that minimum point where the bubble turns around is 10 to the 12 g. Compare that to your roller coasters. And yet the bubble doesn't disappear. It comes back for another helping on the next cycle of sound. How does the light come out now? How do we create the free charges which can then accelerate inside the liquid to generate light? The simplest scenario is the Santa Ana condition. On the days when the wind blows from the desert to the basin, it's 30 degrees hotter in the basin than in the desert. It's hot on a Santa Ana day because, not because the desert is hot, but because the air has dropped from 5,000 feet altitude to 0. And in that drop, the air is compressed, and the work of compression heats up the air. And in the Santa Ana case, the density increases by 10%. In a collapsing bubble, the density goes up almost a factor of 1 million. And so the heating is enormous. The heating rips the electrons off the atoms and creates a plasma. And inside that plasma, there are electrons which are blue and ions which are red. And the electrons, as they accelerate around the ions bouncing around in the plasma, shoot off photons of light which are yellow. So that is the simplest scenario for sonoluminescence. In the case of the 30 kilohertz bubble, the collapse is very, very fast. And so, and in that case, Paul Roberts and C.C. Wu have shown that the collapse launches an imploding shock wave. However, for the demo, which was done on the stage, the Santa Ana condition is an extremely accurate way of describing what's happening inside the bubble. And in the demo that was carried out on the stage, we believe that those flashes of light come from a new state of matter, which I'll say more about in a moment. The spectrum of sonoluminescence is more ultraviolet than the spectrum emitted from the sun. Here you have what a spectrum is. It's the relative amount by which different colors are present in the emission from a bubble. Here's the spectrum from a xenon bubble and a helium bubble. And you can see that the sun tails off, and these spectra continue on. So where the light is ultraviolet, ultraviolet means shorter wavelength, you have much greater emission from sonoluminescence than from the solar spectrum at the edge of the atmosphere. What was surprising to us is that the sonoluminescence spectrum is an excellent fit to Planck's black body law. This is Planck's law. The red line is a fit to Planck's famous black body spectrum, which was one of the founding cornerstones of quantum mechanics. And right here, you can see Planck's constant. Well, this got us excited because this meant somehow quantum mechanics was coming into play, and my advisor always warned me, you must watch out like a hawk to see how Planck's constant enters the science. In this case, Planck's constant is coming in because the absorption of photons is balanced by the emission of photons by the atoms inside this very hot bubble. Planck's law of radiation only comes about when there is equilibrium between the emission and absorption of light. And this, said simply, means that the bubble, to be a Planck spectrum, must be opaque. The key conundrum of sonoluminescence is that if you would take the typical temperature of the sonoluminescing bubble as determined from the fit to Planck's law, from the location of the maximum of the spectrum, you would find, according to standard theory, that the bubble is 10,000 times too small. The bubble is microns in size, and it should be centimeters in size in order to be opaque. So how can this happen? Well, we propose that there is a collective process inside the bubble which is causing a phase transition to a new state of matter where the ionization, the degree of free charge, is so great that the system is obeying Planck's law of radiation. There is, as I said, the first principles don't give us a guide as to any predictability with this phenomenon. They give us principles we have to respect, but they don't tell us the limits of energy focusing that can be achieved with sonoluminescence. So the issue has come up, and it's an important issue. Is there a region in parameter space where we can use sonoluminescence to create such densities and such temperatures that one would achieve nuclear fusion? Namely, can we reach a situation where deuterium is fused with deuterium to create high-energy neutrons? The amount of deuterium in the ocean is unlimited, and this would run all the energy needs for millions of years. This has not been achieved with sonoluminescence. It is a high-risk, high-gain possibility. However, researchers at Purdue did claim that they had succeeded to do this. And
a sacred scientific principle is at stake. The principle of reproducibility.
Nothing is too wonderful to be true that it can't be reproduced in another experiment. And this is what distinguishes science from religion. And so, we applied the merciless principle of reproducibility to the experiments from Purdue in prime time on the BBC, and that was the outtake of my interpretation of holding their feet to the fire. Using a neutron detector which was dramatically superior to the neutron detector which was used at Purdue. This detector was designed and built by Bob Cousins and Brian Naranjo. We found that the level of nuclear fusion was, if it was there, it was orders and orders of magnitude less than they had claimed. However, the pursuit of sonoluminescence, perhaps the pursuit of that region of parameter space where one could find nuclear fusion, is a divine imperative. This was pointed out to me by Rabbi Chaim, the campus rabbi. He says in Exodus 20:18, it says, "V'chol ha'am ro'im et ha'kolot." and all the people saw the sounds. When I showed this at the Ivy Leagues, I got some pushback. They said that, there's no data, it was done only once, and the results were published in book form. And they didn't understand God couldn't get funding. And so at Berkeley, they knew different priorities, and this is Dazzler issue 1, volume 1. I'm converting every nearby radiance into sound. I'm particularly fond of Kirk McDonald's insight that detonation of insensitive explosives proceeds from a little bubble making light. It might be hard for you to see here. This is a street camera of a detonation. So this is time, this is space, and there's a little point of light here. There's a bubble firing when a sound wave hits it to make sonoluminescence, and that bubble is the source of the detonation in the insensitive explosive. And as you all know, Alfred Nobel made his wealth from dynamite. And so Kirk McDonald says, all Nobel Prizes are due to sonoluminescence. The original explanation of sonoluminescence was in terms of frictional electricity. The gas inside the bubble rubbed against the surface of the bubble to separate charge, and you got a spark, much like the sparks you get when you walk across a carpet and touch a doorknob. When you touch a doorknob, the excess electrons in your body jump, hit the doorknob, accelerate when they hit the doorknob, and generate the spark of light. Accelerating charges make the light. And we set up to look into this a rendition of Picard's discovery of the barometer light from 1676. Picard was the president of the Barometers Club of Paris, and walking home on a particularly dark night, he noticed little flashes of light from where the meniscus inside his barometer, where the mercury was rubbing against the glass. Here we have a glass with mercury rotating around the horizontal direction, and there is a beautiful line of light which should be red because we introduced a little neon gas into the system. However, in this case, the frictional electricity is lines, spectral lines, and not the broadband thermal spectrum of the black body sonoluminescence. But my students loved this problem because in German, you could say the whole situation with just one word, Reibungselektrizitätslumineszenz, and they all went off to study German. The frictional electricity is something that goes back to your high school days. You might remember that in your high school classes, the teacher rubbed amber on wool and got a certain charge, and then they used something else, and you had to remember which got positive, which got negative, and depending on the intensity of the education and the science curriculum, you might have had to memorize a table as long as this as to which materials got positive and negative upon contact. Well, George Whitesides points out this table is even inconsistent. If A is negative with respect to B and B is negative with respect to C, you don't necessarily have that A is negative with respect to C. It sort of goes in a circle here, a kind of Möbius strip in contact electrification space. So I ask you, how many of you in the audience asked your high school teacher, how does the charge separate? You know, that's a deep question, because charges are bound by electron volts of energy, and each electron volt is 12,000 degrees Kelvin of energy. Are you really making tens of 1,000-degree hot spots when you rub wool against amber? I don't think so. So how is the charge separated? Well, the answer is that there is still no first principles theory of contact electrification. It's absolutely not known. Here you have Bernoulli addressing the French Academy in 1700, saying it's still 30 years since Picard discovered the barometer light, and we still don't know how it works. Here's Dan Rugar saying, despite its everyday occurrence, the physical explanation of contact electrification has eluded researchers since the time of the ancient Greeks. Is the static electricity due to transferring electrons or transferring ions? Even today, 2008, scientists can't agree for the same system what the origin of static electrification is. For us, the first principles, there's no, in material science, there's no ab initio theory starting from the first principles to determine contact electrification. That means it's ripe for discovery. And so, for us, the vector for discovery comes in a paper by Abramov, where he says if you split mica in the dark, it becomes luminescent. This was well known. It's called triboluminescence. But if you go to a high vacuum, the glass of the vessel fluoresces like an X-ray bulb. So Abramov was saying in 1930 that splitting mica apparently was a route towards X-rays. This would mean that triboluminescence from contact electrification is the tale of a much more energetic spectrum that extends to X-ray energies. Here's the electromagnetic spectrum again, going from the radio out to the gamma rays. Here are the photon energies. 1 volt is about the visible, 10,000 volts is the X-rays, and gamma rays can be millions of volts of energy. So here, Abramov's paper triggered a line of research in the Soviet Union that was never reproduced in the West. And furthermore, some of those researchers got swept up in the cold fusion scandal of 1989. And so we looked into this, and we started with Scotch tape. And here is triboluminescence from peeling Scotch tape. You can do this at home in the dark. Take a roll, let your eyes adjust, and peel it, and you'll get this beautiful line of light. If you now put it into vacuum, you then find, here we're using what's called a scintillator. A scintillator is a crystal which responds to high-energy particles. And when the high-energy particles hit it, it turns that into light. The scintillator, when you're peeling Scotch tape, makes enough light in order to take this picture. Here, some neon has been introduced into the chamber, so it glows red from all the energy that's stirred up, exciting the neon atoms. But in the center, you can see a little line of ultraviolet blue light in addition to the red from the neon. And that blue light is the source of X-ray emission from the peeling tape. Furthermore, the X-rays come out in nanosecond pulses. That means you get bursts of X-rays which are about 1/billionth of a second long. The spectrum of the X-rays extends out to about 50,000 volts. So peeling Scotch tape is doing the same thing as using a 50,000 volt power supply to generate X-rays in a dentist's office. It raises a wonderful question. Here is a photo of the meniscus of the vertex of the peeling tape. Look at how complex is this tangle of adhesive. How does the weakest force in chemistry, which is the van der Waals force, lead to all this organized charge separation and nanosecond X-ray pulses with 1/10 of a millimeter, 100 microns of spatial coherence? Did you ever try to buy an X-ray source which has 100 micron spot size and nanosecond pulses? This is an interesting commercial device. But if we're right that the spot size for the emission of the X-rays is only 100 microns, you ought to be able to cut the tape down to a millimeter and peel a millimeter string of tape and still get nanosecond pulses. And of course you do. This is the world's smallest source of nanosecond X-ray pulses from Scotch tape. as I've emphasized, this phenomenon, as amazing as it is not tethered in the first principles of physics. That means you can ask the question, can we do better? Can we double the energy? Can we double the flux? And in the spirit of doing better, we have a second, much more risky demo that Dr. Carlos Camara will perform for you. Now, I'm wearing my radiation badge. This experiment and the previous experiment, you know, the one where we had the $50 tube to generate the flashes of light, and then we needed $2 million to measure it. This experiment has a chance of going bad. The students love that. When you do a demo in a physics class, the students love it when the demo doesn't work. And I hope you'll be as understanding. What we have here, in the spirit of discovery, there's no Scotch tape. This is a roll of plastic. There's no adhesive. This is a piece of lead foil wrapped around a roller. And one is simply taking the lead foil and rolling it against the plastic inside of a vacuum system. Are we, okay? So here's a Geiger counter. I did want to tell you, I informed Chancellor Block of this earlier, that these experiments have all been certified by Campus Radiation Safety. So I'm going to hold this here as the experiment turns on so that you can see that there's no radiation coming into the audience. Okay, now that you're relaxed, and here's my radiation badge. Let's come in here. Okay, I think we've made the point. Oh, are you able to get the scintillator? There is a scintillator, but I think the floodlights are too strong in order to see the bluish glow of the scintillator on the screen. Can they dim the lights momentarily? No. Okay. There we go. Oh, there you. Yeah. Oh, that's great. Okay. Okay. Thank you, Brian. And that's Dr. Camara. That was great. So I was talking about sonoluminescence at Georgia Tech. And I was discussing the electrostatic explanation, which of course is very interesting in its own right, but is not the explanation of sonoluminescence. And a professor there, Ahmet Erbil, jumped up and said, hey, if you're interested in these energy focusing phenomena, why are you studying sonoluminescence? I mean, you should be looking at ferroelectric crystals, lithium niobate, lithium tantalate. And I'm sorry, you should be looking at ferroelectric crystals, and in his case, it was triglycine sulfate. And I said, what do you say when you're in front of 200 people and someone says you're doing the wrong direction of research? I said, well, where is it published? What you can do with these systems. And after the talk, he showed me this paper by Hans Riga, where they heated triglycine sulfate by tens of degrees above room temperature and generated the emission of 30 kilovolt electrons. And 30 electrons with an energy of 30,000 volts. And to me, that was a eureka moment, because if you could, by heating a crystal, generate those kind of potentials, if you could do a little better, you could use it to generate nuclear fusion. We tried very hard to reproduce those experiments and got nowhere. And then I got into touch with James Brownridge, who said that triglycine sulfate was a bad crystal to work with, and you should use lithium niobate and lithium tantalate. And with those crystals, we set out to reproduce the Riga experiments and to search for nuclear fusion using crystals. So if a crystal can generate 30,000 volt X-rays by accelerating electrons, then if you could accelerate the ions, which means the deuterium, to higher energies, but not much higher energies, you could then generate nuclear fusion, and here is the famous reaction. Here is the apparatus. The key advance is from Jim Chimchevsky, who said you got to put a little tip on the system. So let's first review how you get the X-rays from lithium niobate, and then we'll see how you can get the fusion. Here you heat it. You have a negative surface here generated by the heat. The electrons are repelled by the surface charge, hit a target, and make X-rays. The goal now is to reverse the polarity, which means to cool instead of heat, and then to put a tip on the surface so the tip would act to break up the deuterium molecules into deuterium atoms, and then to accelerate the deuterium into a target to create the nuclear fusion. Now here's Brian Naranjo, who ran the experiment, and you can see that changing the temperature by 40 degrees led to a large count of neutrons coming out of the system for the crystal immersed in deuterium. So I tell my colleagues, I can build for you an egg-shaped device which has a crystal inside and some deuterium gas, and I plunge it into ice water and then warm it with my hands, and I can make dangerous quantities of nuclear fusion from that non-intrinsically radioactive device. And my colleagues say, so where's the physics? Because if you take deuterium and accelerate it with 100,000 volts of energy into a target, you're going to get fusion. And of course, the physics is in the material science. Why does it turn out that these materials have these amazing properties? For instance, lithium niobate, if you made it in vacuum by melting together lithium oxide and niobium oxide, when it comes out, a cubic centimeter piece has a potential of 15 million volts. Now, of course, when you take it out of the vacuum, whatever charges are in the air neutralize it and collect all over the surface. But the physics is in the material science. How does it turn out that this is the case for this material? And I'd like to show you roughly what the picture is. Think of a simple sodium chloride type lattice with positives and negatives. Then the positives and negatives are the ions. The springs are the forces between the electron clouds of the nearest neighbors. The springs repel them from getting too close, and the positive and negatives cause it to attract. When the force of the attraction is bigger than the force of the repulsion, the system distorts in such a way as to make a separation of charge, which leads to the spontaneous polarization of these crystals. What stops the crystal from going to an infinite charge separation? This is due to the short-range forces. And the short-range forces are extremely complicated, and people have 15 different methods for dealing with it because it's controversial. So the first principles almost gives us a picture of how the system becomes ferroelectric, how it develops a huge potential and a huge surface charge, but then we get into the complex domain of the short-range forces, and we're outside the realm of predictability. But in this case, there is a courageous man. In 2007, Ron Cohen at Carnegie Institute, Washington, proposed to predict a new crystal, which is a first for this field, yttrium silicon oxynitride, which, if it was made according to his formula here, would be almost 10 times stronger than lithium niobate and have a field of 100 million volts per centimeter. A cubic centimeter crystal would have 100 million volt potential when freshly made. The jury is still out on this. So what's the sonoluminescence good for? What is the triboelectrification good for? Sonoluminescence, which is this unknown phenomenon, has been used to calibrate detectors for high energy physics. It gives a beautiful spherical flash of light, which when it hits the photomultiplier tubes, sets up a synchronization in time for the tubes used to look for neutrinos. This is a 1 millimeter rod vibrating up and down, making sonoluminescence. It's used for ultrasound-assisted lipectomy. Jonathan Hurd in my lab is going the next step with the Tribo X-ray source, and instead of rollers, just bringing surfaces together and measuring X-rays as you just bring surfaces together and apart, and trying to build a flat panel X-ray machine which has no high voltage power supply and could take a pixelated X-ray picture. So let me now step back and get to the key point of what I want to try to communicate today. I want to look at a simpler system than the transdisciplinary objects we've been looking at, where you start at one energy and end up at other energies and end up at plasmas. Let's just look at the equations at the phenomenology of fluids. How do fluids move? Fluid mechanics is the discipline that studies waves in the ocean, studies how surfboards work. Here you have solitons in the Andaman Sea, isolated waves photographed from a satellite marching across the Andaman Sea. Here's a raindrop hitting water to make a vortex ring in the water. Here you have convective turbulence. This is an extremely heavily studied topic. I'd like to show you what's happening here. You heat a liquid from below, and hot plumes rise and cold plumes come down. These systems at higher and higher temperature gradients can become extremely turbulent. Yet, no one questions sound waves, shock waves, how planes fly, solitons. Turbulence is all described by the equations of hydrodynamics. But hydrodynamics is not the first principles of physics. Hydrodynamics is a set of equations which physicists struggled for over 100 years to come up with a really good set of equations that is now written in stone. But it's not the first principles. The first principles are Newton's laws for the interacting molecules. If you know how the interacting molecules are working together, why do you need hydrodynamics? Why don't you just solve Newton's laws? So there's also a lot of work trying to connect Newton's laws for interacting molecules to hydrodynamics. And this has never been achieved. Hydrodynamics has never been derived from Newton's laws. Again, the first principles of physics don't show us how to approach many phenomena around us. I am prepared to argue, but not today, that the equations of hydrodynamics will never be derived from Newton's laws for fundamental reasons. And so I am interested in many of the systems we study today because they might share a common thread. They might be striking and important phenomena which are nevertheless unapproachable from the first principles. And this reminds me, or takes me to the insight of my advisor: the frontiers of physics are all around us. Thank you. course, of course.
Thank you so much, Seth, for that, dare I say it, illuminating presentation to all of us. The talk is now open for questions, and I think we have microphones available if anyone would like to field a question, ask a question.
Yeah, thank you.
Thank you for the interesting talk. And maybe I didn't catch well for the part that you're using Scotch tape to generate the X-ray. So it's also happening in the vacuum, or both can be in
the Scotch tape making X-rays happens in a vacuum. That doesn't mean that there won't be some system which is particularly strong in its energy, charge transfer, that it couldn't happen outside of a vacuum. But so far, we've not found a system that works outside a vacuum.
That's maybe good, because then the pregnant woman will pay attention to play with the Scotch tape.
I thought you were going to ask about the physical therapy device.
So you mentioned that the hydrodynamics could never be derived from fundamental equations, I guess. I thought that there was a tradition in physics which is sometimes referred to as emergent phenomena, and which is, in my somewhat primitive understanding, is that you start with some system which you would just think of as fundamental, and then you apply basic fundamental equations with the use of very large machines that you can simply bash them over the head with, and eventually you come up with some simple phenomenon that come out of it. Now, would you say that hydrodynamics could be derivable in this sense, or would you go further and just say that?
I would. First of all, emergent phenomena I stayed away from that word. It's entirely appropriate for you to bring it up. But I stayed away from that word because it's too big a catch basin for too many concepts. But certainly, if properly, if carefully defined, it could strongly overlap with the point I was making about hydrodynamics. However, the reason that the Navier-Stokes equations of hydrodynamics will never be derived from first principles has, in any controlled approximation, arises from fundamental nature of interactions between particles on long time scales. And I would prefer to stick to those precise situations than to say that something comes out in some large limit. How are you approaching that large limit? But you're entirely, it's entirely justified to try to look at it from that point of view.
Seth, does the character of the emitted light in sonoluminescence depend, or how does it depend on the frequency of the sound that you put in? Like, for example, if you use ultrasound.
The spectra which we observe, and we've observed spectra ranging from 40 hertz sound waves, 40 cycles a second, up till about 1 million cycles a second. The spectra which we observe are within a relatively narrow range, say from, well, we have to be careful here. At the ultrasound range in the tens of kilohertz, the spectra are about 10,000 degrees, and that persists down to about 40 hertz. And those are black body spectra. When we go to 1 million cycles a second, the spectrum is no longer a black body. So we're comparing a different type of spectrum. And if you let us, at 1 million cycles a second, put in a theory of transparent plasmas rather than black body plasmas, we then get to 1 million degrees as the spectrum. But we've changed to a different type of spectrum, which requires a different type of theory. And so there's an issue as to the extent, to how can the theory be justified in this case? Yeah. Yeah.
Since, as I understand it, you've produced some fusion, how optimistic are you about that there might be some practical energy source this way?
It's interesting to produce fusion with heat, because heat is a waste form of energy. But heat also is a very high energy content form of energy. Right? The amount to raise the temperature of something by a few degrees is an enormous amount of energy. And so the amount of fusion we get relative to the heat is absolutely tiny. The trick would be to figure out some high Q system where you put in mechanical energy to generate these effects and make the fusion. Then you could recover many orders of magnitude, but we don't know how to do that. But I think the inspiration might be from Philo Farnsworth, who was the inventor of television, and he spent the last part of his life trying to figure out better ways to use mechanical energy to get to nuclear fusion. He has patents on that. Yeah. Thanks.
Well, thank you once again for this really stimulating lecture, Seth. We really enjoyed it, and I now invite all of you to join us for a reception outdoors. Again, thanking Seth for a really illuminating presentation. Thank you.
Thank you.
Videocassette copies of this program are available for purchase from the UCLA Instructional Media Library. Call toll-free 1-877-958-2200. Additional information about the people, places, and ideas discussed in this program is available at our website, www.webcast.ucla.edu.